All right. Hey, AP Chemists. This is our summer work important information part 3. This is going to be our 7th video lecture series of this. This is going to be another topic that I skip in the beginning of the year. So I'm going to skip this in September and assume you could do it. This is determining a chemical formula from experimental data. This is another very important calculation. This is like calculating molar mass or even percent composition, but now tying those two together to get chemical formulas. Something that's very important to remember is this law of definite proportions, right? So for example, if I have carbon dioxide, CO2, that has 1 mole of carbon for every 2 moles of oxygen, or there are 1 carbon atoms for every 2 oxygen atoms. If I do the calculations, I would get 28% carbon for 72% oxygen. Always, always, always. If I find a compound and it's 72% oxygen and 28% carbon, it has no choice to be CO2 or have a 1-to-2 ratio of carbon to oxygen. I'm going to repeat that because that's going to help you with our calculations. If I have carbon dioxide, CO2, the ratio of percentages will always be 28% of carbon for 72% oxygen, always, always, always. Those percentages will always give me the ratio of 1 mole of carbon for every 2 moles of oxygen and the formula CO2. Now let's work backwards. What if I give you the percentage data or the data of the mass of each element and I want the formula? So if we decompose water into hydrogen and oxygen, we can measure the masses of hydrogen and oxygen produced and then determine its empirical formula. So suppose we decompose a sample of water. We know the answer is going to be H2O. But let's say I did not know that. We know we should get H2O. How are we going to get that? What is the empirical formula? Let's say I decompose. Decompose means I take H2O and I break it into hydrogen and oxygen. Sorry, you cannot see that. I have H2O, and I break it into hydrogen and oxygen. All right, I break it into its constituent elements. And find that it produces 0.857 grams of hydrogen and 6.86 grams of oxygen. And I ask, what is the empirical formula? Now, Mr. T has a way. There is a methodology that I will continuously and always use in order to do a question like this. And I kind of have it broken down into 4 major steps. If I'm given percentages of each element in the compound, I need to turn those to grams, or I need the grams of each element. So that's what I call step 1. Then I take those grams and I want the ratio of atoms. So I need to convert those grams to moles. That's step 2. Once I have the moles of each element, those are going to be the ratio of moles of each element in the compound. I'm going to divide by the smallest moles to get the empirical formula subscript numbers. So my 3rd step is dividing by the smallest moles. And then my 4th step is using those smallest moles that I get, which hopefully should be whole numbers. I'm going to write those as subscripts to get my formula. So I kind of just summarized my steps here. I'm going to show you how to carry them out now. So I have 0.857 grams of hydrogen and 6.86 grams of oxygen. Write down or calculate as given the masses of each. This is where I have to say calculate. Percentages, I'm automatically going to turn to grams. So if I had and I did that on my previous lecture, so I'm going to jump back a bit to the magnesium sulfate one. If you look at my magnesium sulfate, I'm going to highlight it in orange here. These percent compositions can be used as conversion factors. So if I had 100% of magnesium sulfate, that's 20.2 grams of magnesium, 26.64 grams of sulfur, and 53.17 grams of oxygen. If I had 100% or 100 grams of magnesium sulfate, I could pretend 100% is 100 grams. I could instantly convert those percentages to grams. Keep that in mind. That'll be for the next page. Let's go back here, though. So write down or calculate as given the masses of each element present in a sample of compound. If you are given mass percent composition, assume a 100-gram sample and calculate the masses of each element from the given percentages. So I need percentages, grams. In this case, I don't have to worry about percentages. I automatically already have grams. So I have grams. Great. So I'm done with my step 1. Step 2. And don't be confused by this percentage. I wasn't given percentage. I could say I have 11.1% hydrogen and then 89% oxygen, and then I'd be doing something else. But I don't have that. I'm going to go back to the masses that I have. Convert each of the masses in step 1 to moles by using the appropriate molar mass for each element as a conversion factor. So I had 0.857, I'm going to use highlighting. I have 0.857 grams of hydrogen. Whatever I'm given, grams goes on the bottom, 1 mole on top. I'm dividing by that molar mass. I get 0.85 moles of hydrogen. I have 6.86 grams of oxygen. I divide by the molar mass of 16. I have 1 mole on top. I get 0.428 moles of oxygen. And now it says, and this sometimes I like doing this to remind me that I'm looking for a formula. It says write down a pseudo formula. Now you don't have to do this. You might see me work and skip to divide by the smallest moles. But I like to write a pseudo formula. H.850 O 0.428. Right, so I use these moles as little subscripts. This is not how we write chemical formulas. We use whole number subscripts as chemical formulas. But I'm going to show you how we could get there. We get there by dividing each of these numbers by the smallest moles. If I divide both of these numbers by the smallest moles present, that's going to give you my whole number ratio. Between 0.85 and 0.428, I'm going to divide both of them by 0.428. So divide both by 0.428, and I'm going to get H2O1, which I could just write that as H2O. And this is my empirical formula. Done. This has 2 hydrogens for every 1 oxygen, or 2 moles of, 2 moles of hydrogen for every 1 mole of oxygen. This 0.428 is approximately half of the 0.85. So this works. 0.85 over 0.428 is approximately the same as 2 over 1. Hydrogen to oxygen. Hydrogen to oxygen. And so before our eyes, I'm able to write an empirical formula. Remember, an empirical formula is the simplest ratio of atoms. And I'm proven that the empirical formula of water is H2O. And this happens, and it's going to happen on the next page, if the subscripts are not whole numbers, right? I can't round. I could round 0.1 to approximately 0. I could round 0.9 to approximately 1, or like the next whole number. But anything in between is a little iffy. If the subscripts are not whole numbers, multiply all the subscripts by a small whole number from this table to get whole number subscripts. I would suggest remembering 2 of these. I would say the 0.5 is good. 0.2 is good. Even the 0.3 is good. Actually, that's very large. You can't see that. So here are the ones that I would suggest you remember. I would remember if I get 0.5 in my decimal, I'm going to multiply everything by 2. If I get 0.33 or 0.3, I'm going to multiply everything by 3. If I get about 0.2 in my decimal, I'm going to multiply everything by 5. So I have some examples of that. Let's look at the next page. I have more examples. Best thing to do is example, example, example. So I have 2 examples here. So it says a compound containing nitrogen and oxygen is decomposed in the laboratory. It produces 24.5 grams of nitrogen and 70 grams of oxygen. So not percentages, right? Look at example 2. I give you percentages. I'll do that next. But I've automatically given the grams. So I'm going to use that. Write down the masses. Then I'm going to convert these masses to moles. And I did that already. I kind of skipped a couple of steps here. Saving some time and you don't have to watch me write everything. I converted these grams to moles. Typically, you're dividing by the molar mass, or I'm doing dimensional analysis as I've done in a previous lecture. And now I have 1.75 moles of N for every 4.375 moles of O. I'm going to write a pseudo formula, N 1.75, O 4.375. But of course, this is ridiculous. We don't write formulas like this. I'm going to divide these subscripts by the smallest moles, or the smallest subscript. I'm going to divide it by 1.75. 1.75 divided by 1.75 is, of course, 1. 4.375 divided by 1.75 is actually 2.5. Now, I actually did write this over here. The example is NO2.5. Here's where the 0.5 comes in. If I end up with a 0.5 as part of my subscript, so 2.5, 3.5, 4.5, this is not a whole number. And you cannot round to 3 if it's 0.5. So what I'm going to do is I'm going to multiply everything by 2, and I'm going to get N2O5. 2 to 5 is still an empirical formula. I cannot simplify 2 and 5 further, right? It's kind of saying, like, what's another way of writing 2.5 over 1? Well, 5 over 2 is the same thing as 2.5 over 1. For every 2 moles of N, there are 5 moles of O, which is the same thing as 1 over 2.5. 1 over 2.5 moles O, moles N. These are the same things. Okay? And so my correct answer would be N2O5. That would be my empirical formula. And again, following these 4 major steps, make sure you have the masses of each element, right? Convert each mass to moles, divide by the smallest moles, write those subscripts as whole numbers. Let's do another example in which I actually use percentages now. All right, so a laboratory analysis of aspirin determines the following mass percentage. This is typical. There are instruments that if you put a sample through, it automatically just gives you the percentage of each element. So this would be more useful in the lab. So I have 60% carbon, 4.48% hydrogen, and 35.52% oxygen. Now look here. Write down or calculate as given the mass of each element. If you are given mass percentage composition, assume a 100-gram sample and calculate the masses of each element. In that case, the percentages are just equal to the grams. So if I have 60.00% carbon, that means I just have 60 grams carbon. 4.48% hydrogen just means I have 4.48 grams hydrogen. 35.52% oxygen just means I have 35.52 oxygen. Right, so here I am in the steps that I know before. Then my next step is converting those grams to moles, and I did that already. Divide by the molar mass. I get 5 moles carbon. I get about 4.48 moles hydrogen. I get about 2.22 moles of oxygen. Right, so carbon, hydrogen, oxygen. I'll write a pseudo formula, or I'm going to divide all of them by the smallest moles. C5, H 4.48, O 2.2. It is obvious that my smallest moles here is 2.22. I'll divide all of them by 2.22, and I will get C 2.25, H 2.2, 2, H2, and then O 1. And now I am not left with whole numbers. What do? If the subscripts are not whole numbers, multiply all the subscripts by a small whole number. See this table. I have 0.25. If I have 0.25, I'm going to multiply everything by 4. And so I'll take everything here, multiply it by 4. If I do 2.25 and I multiply it by 4, I'll get 9. If I take 2 times 4, I get 8. If I take 1 and I multiply by 4, I get 4. Boom. Empirical formula. 9 to 8 to 4 is an empirical formula. It cannot be simplified any further. Those are ratio in the simplest form. Okay? So I purposely did some tougher questions in which I don't get whole numbers. in most cases, especially in the AP exam, or especially if I give you most examples, you'll probably end up getting whole numbers, kind of like what happened in H2O here. We got a 2-to-1 ratio, we were done, it was good to go. Now, we also learned about molecular formulas. So I just did 3 examples with calculating empirical formula from mass data. How would I get a molecular formula? Well, recall, an empirical formula is the simplest ratio of atoms in a formula. A molecular formula is a number larger than an empirical formula. So, for example, if I have the empirical formula C2H5, if I multiply every subscript by 5, I will get the molecular formula of C10H25. This is a molecular, and this is an empirical. And we did this earlier in this series lecture. We can find the molecular formula of a compound from the empirical formula if we also know the molar mass of the compound. So keep in mind, the molecular formula is an empirical formula times some whole number. N is a whole number that we figure out. Whole number we calculate. The molar mass is the empirical formula molar mass times this whole number. So if I had an empirical formula of CO2 and I multiply by 4, the molar mass would be C4O8. It would be of this molar mass. It would be 4 times the carbons, 8 times the oxygens. Therefore, if I want to get N, I take the molar mass of my given compound. This is typically given in the problem. And I divide it by the molar mass of the empirical formula in which I have to calculate. And that's going to be my whole number that I use. Now, I might have over-explained, it seems like a lot, but the best thing we could do is do an example. So here's a guided example. The empirical formula of butadiene is C2H3O, right? 2 to 3 to 1 is the simplest ratio. And its molar mass is 8609. This does not have a molar mass of 8609. The molar mass of the molecular compound is 8609. This is what I mean by the given in the problem. The molar mass of the molecular is 86.09. Determine its molecular formula. Well, the first thing you got to do is I need the molar mass of the empirical formula, and I kind of already did this for you. 2 carbons, 3 hydrogens, 1 oxygen. 2 times 12 is 24, plus 3 is 27, plus 16 is about 43. That is the molar mass of the empirical formula. If I want to figure out and be able to use molecular formula is the empirical formula times N, I need to get N. N is equal to the molar mass of the given molecular formula divided by the molar mass of the empirical, which we just got. Well, I have that. I have 86.09 grams per mole, which is the molecular, divided by about 43 grams per mole, which is the empirical, and you wouldn't believe it, I get a whole number, 2. There is my N. So now if I want my molecular formula, I'm going to take this 2 and multiply it by my empirical formula. So 2, right? I'm doing this right here. My molecular formula is my empirical formula times N. So N, which is 2, times C2H3O2. Sorry, not O2, sorry. Oh, I multiply all of the subscripts by 2, and I get C4H6O2. This is my molecular formula. So to quickly summarize this, because you do have a couple of questions like this, you have to be given a molar mass, which is you're going to assume is the molar mass of the molecular formula. You're going to have to determine or given the empirical formula. This is like from before, right? Maybe I won't do this. Maybe I'll give you all this, and then I'll say, oh, the molar mass of the molecular is some number, right? So I give you this data, and then I say the molar mass is something, right? So you might have to use mass data or percentage data, and then be given the molar mass, and then do all that work. Here's a sample AP Chemistry content question. I'm not going to do all of it. I'm actually going to say this. If you get the gist of this, you could begin starting on your exercises here. You could do the AP Chemistry content sample question. This is going to show up on your basics quiz, an example like this. And exercises 18, 19, 20, and 21. If you get the gist of this and want to start trying to do the practice, I would end the video here now. Otherwise, stick around and do some examples with me, and then you can do the rest of the examples on your own. And to remind you, you are just turning in the exercises 18 through 21 for this lecture summer work here. So you're not turning in the notes, you're just turning in the answers to the exercise problems to show evidence that you understand. All right, if you're still with me, let's do some more practice problems here. So determine the molecular formula. So now this is going to be just like what I just taught you up here in the guided example, with a compound with a molar mass of 60.110. So this, I give you the molar mass later. And the following percent composition. I give you 39.97% carbon, 13.41% hydrogen, 46.62% nitrogen. Okay? And so now I'm going to do the math here. My first step, this is where I don't have the box now. My first step is convert these percentages to grams. I already did that. Boom. Convert my percentages to grams. Then I'm going to do my second step. Do you remember the second step? Convert, that's right, convert my grams to moles. So 1 mole of carbon, 12.0 grams carbon, 1 mole hydrogen, 1.08 grams hydrogen, 1 mole nitrogen, 1.008, oh, sorry, just keep on quickly doing it, 14.01 grams nitrogen, boom, 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 and I'll get my math here. I'll get 3.33 moles of carbon, I'll get 13.33 moles of hydrogen, and I'll also get 3.33 moles of nitrogen. You might be able to see a formula forming before our eyes here. So I'm going to make my pseudo formula. This was step 2. Now I'll do my step 3 here, my pseudo formula. C 3.33, H 13.33, N 3.33. I'm going to divide all of these by my smallest moles here. I'm going to divide all of them by 3.33. You could also, of course, do that over here, dividing all of these by 3.33. And you'll get 1C, 4H, 1N. C, H4, N. And I'm actually going to erase these ones because we don't typically write ones in empirical formulas. But boom, this is my empirical formula. But I did not ask for the empirical formula. I asked for the molecular formula. Well, if I want to get the molecular formula, I have to do the steps that I just showed you in the previous part of this lecture. All right, again, we need the empirical formula multiplied by some number n. If I want to figure out what this number n is for my molecular formula, I need the molar mass of the given compound, which I gave you is 60, divided by the molar mass of the empirical formula. I'm going to have to calculate that. So CH4N is 1C plus 4 H's plus 1 N. That's 12.01 grams plus 4 times 1.008 grams plus 14.01 grams. If I do all that math, this is approximately 30 grams per mole is the molar mass of the empirical. Let me get my N now. N is going to be the molar mass of the molecular divided by the molar mass of the empirical. And you wouldn't believe it, the math works out very nicely here. 60.10 grams divided by approximately 30 grams. This gets approximately 2 again. It's not always going to be 2, but the examples I made, I just try to get 2. So now if I want to get my molecular formula, I'm not done. Do you see how much work this was? It's going to be my N times my empirical formula is my molecular formula. EF is empirical formula, MSF is molecular formula. So I take N, which is 2. The empirical formula is CH4N. 2 times the 1 carbon, 2 times the 4 hydrogens, 2 times the 1 nitrogen. I get C2 H8N2. That is the answer for this worked AP style problem here. Boom, done. Right? Whew! A lot of steps. But if you gain practice in the exercise here and you keep on doing it over and over again, you're going to remember the steps and you're going to be very successful in being able to do these calculations. All right, I did do some of the work for your exercises here. Again, you don't have to watch the rest of this lecture here, but this is if you want to get a little bit more help and extra practice in doing them. You are responsible for doing questions 18, 19, 20, and 21. For 18, it says, a chemist decomposes a sample of several compounds. The masses of each element are listed. Calculate the empirical formula. So again, don't forget the steps. First step, percentages to grams. Second step, grams to moles. Third step, divide by smallest moles. And then fourth step is writing your formula, making sure it's there. Sometimes 3 and 4 happens at the same time. So I did most of the steps for letter B here, and I kind of helped you out. The molar mass of barium is 137.33. The molar mass of bromine is 79.90. I have 2.677 grams of barium, 3.115 grams of bromine. Convert those to moles, boom, I got my moles. And then I write my pseudo formula here. And then I'm going to divide both of them by my smallest moles, which ends up being 0.01949. 0.01949. And then this gives me some nice simple numbers here. I get BA1. BR is going to be 2. Done. This is barium bromide, by the way. Barium bromide. It's an ionic compound. It has a metal and a non-metal, and that's consistent with our nomenclature rules. All right, 19. This one just wants empirical formula. I did most of the steps for us here. So I'm going to do 19B, vanillin, responsible for the taste and smell of vanilla. I have 63.15% carbon, 5.3% hydrogen, 31.55% oxygen. So I have my moles here. I automatically converted those percentages to grams, so done. I converted those grams to moles, done. I have my moles. Now I'm going to divide by the smallest moles. I'm going to show you another way here. I'm just going to quickly divide all of these by the smallest moles of 1.97, 1.97, 1.97. Hopefully you see that the smallest moles here is 1.97. So I divide all of them by 1.97. Sorry, just trying to get my calculator going again. So I do 5.26 divided by 1.97, and I get about, wait, did that work? 5.26 divided by 1.97, and I get about 2.67, and 1. Now, look at this. This did not end up being whole numbers here. So I'm going to go look at my table here and see what happens if I get 6.6 or 6.7. Look at this right here. If you get the 0.66 or the 0.67, I have to multiply everything by 3, right? So this is what happens when you don't get those whole numbers. So I have C 2.67, H 2.6701. I'm going to multiply everything by 3. If I do that, I get approximately C8, H8O3. That is a nice empirical formula. 8 to 8 to 3 cannot be simplified further. All right, and then the last one I'll go over. 21 is, 21's a doozy. This is an AP intense style question. And look, I have the periodic table here for you. It says a metal forms a compound with the formula MCl3. That means 1 mole of M for every 3 moles of Cl is in this compound. Hint, hint. I have 3 times the amount of moles of chlorine than I do this metal M. If the compound contains 65.57% chlorine by mass, what is the identity of the element? Whew! This is like an intense AP style question. I have seen this on the 2014 exam where you weren't allowed to use the calculator. That has changed since then. Okay, so I'm going to remind you about percentages. I could take those percentages and convert those to grams. If I have 65.57 grams of chlorine, and I just have this metal and chlorine, that must mean I have 34.43 grams of this metal. So I started kind of doing the beginning of the calculations here. If I have 65.57 grams, I convert those, this will be my first step, I convert those to moles, and I have 1.85 moles of chlorine. So M, some subscript, Cl, 1.85. And then if I had 34.43 grams of this metal, I don't know how to convert it to moles, but I could tell you how many moles I should have. I should have 1/3 the moles of Cl. Why? Because for every 1 mole of the metal, there are 3 moles of the chlorine. So I'm going to have 1/3 the moles of the metal. So this is nice and clever here. This is a clever way to do this. I am going to have approximately 1.85 divided by 3. I should get 0.617 moles of this metal. M 0.617, Cl 1.85. This would be MCl3. But how am I going to figure out the identity of this element? Well, I know that this metal, 34.43 grams, must equal 0.617 moles. I've identified how many moles must be in this compound because for every 3 moles of chlorine, there's 1 mole of this metal. Well, if I have 34.43 grams of this metal, that corresponds to 0.617 moles. Molar mass is going to help me. Now, this is the first time we're seeing something like this. But remember, units for molar mass are grams per mole is molar mass. I could actually identify the molar mass of this metal if I take this grams and divide by this moles. So if I do 34.43 grams of this metal, and that corresponds to the 0.617 moles of this metal, I get 55.8 grams per mole. And that means the identity of this element, M, is Fe. And the compound is FeCl, iron, Roman numeral 3, chloride. Now, there's another way that I could figure this out. Well, remember, grams divided by molar mass is equal to moles. That's a nice little trick there. I could rearrange this and say grams divided by moles is equal to molar mass. So it's a nice little trick. If I have the grams and I know the moles that corresponds to, if I divide the two of them, I get the molar mass. Okay. All right. If you have any questions, comments, concerns about calculating empirical molecular formulas and needing a little bit more help with this, reach out, message me in the Remind, email me. Otherwise, turn in the work that you know how to do.